So, last time when we got together, we started talking about the nature of memory. And we were talking about physical memory at first, and we discovered something horrible about physical memory. Does anybody remember what it was?
You have access to DOS.
You have access to everything. There's no protection, there's no nothing. Okay, all there is raw memory. If you can generate an address for it, you can access it. Okay, that was kind of ugly. And then what we said was, we talked about why that was reasonable at the time. And then we said, well, gee whiz, what if we want to, for example, have more than one process in memory? And we talked about how how just painful that is for programs that still use physical addresses. And at that point, hopefully, we motivated each other to say, I've heard of this thing called virtual memory. Why don't we just go run that? So what we did was we talked about writing programs that begin at address 0 and went to some maximum number. And that looks like the CS201 definition of virtual memory, doesn't it? And we accomplished that with some hardware. What was the one thing we had to add to the hardware to make this work? We had to add a register, didn't we?
Oh, yeah.
Okay. And so there was a base pointer. We started off with fixed size segments. And we said that the process is currently in the CPU. We will load its base register into the CPU. We call it a memory management unit, but it's a simplified memory management unit. It's one register big. It'll get friends before too long. And we said every time you translate an address to physical memory, you will translate it by taking the reference address and adding the base register to it. And we said, well, those were virtual addresses. Because they pointed into an idealized process space, didn't they? So we call them virtual. Just like we virtualized the CPU. Now we're going to virtualize memory. Strangely enough, one of the big benefits is that it simplifies the programming model. Okay. Now, by doing that one simple step of a simple base register, we got something wonderful. And what was that? It has to do with multi-programming. We got segmentation out of it, that's for sure, but we got a specific type of segmentation. I'll start it, someone else finish it. We've got segmentation with no
variance in size?
Well, no variance in size, but that's just what we got. There was a benefit from that.
External fragmentation, is that?
Say it again?
External fragmentation?
External fragmentation. What's external fragmentation?
Memory that's inaccessible by any process.
So yes, so it's memory is not accessible by any process, or just it's external to all processes. Okay. Can't be allocated to a process. By making everything power 2, though, we were able to say, hey, all powers of 2s are the sum of other powers of 2s. So we can get what's called perfect packing. But it came with a problem. What was that problem? Well, yeah, so the fixed size memory wasted a bunch of room, but why did we waste a bunch of room? Okay, that's one way of saying it, but I'm gonna push for a more rigorous statement. It's a way of looking at it. I want to look at it a slightly different way because it shows up later in this lecture and next lecture.
This size is optimized for the voice space.
Yeah, it had to be set to the worst case. And setting it to the worst case had two very interesting side effects. Okay? One was that you could have no jobs bigger than that segment. Okay? All right, you were limited. Didn't matter, you were limited. Size of segment. And there were lots of programming tricks we used to deal with that. Overlays, and, comma blocks, stuff like that. The other thing that came along with it was that because we had to allocate for the worst case, we didn't have good allocation for the common case, did we? And the common case used about how much of that fixed size segment?
10%.
About 10%. Okay. Right? In a 64-bit system, it's way worse. Okay. Well, actually, 2 to the 32. But we said, well, gee whiz, what step could we take to actually get back some of that memory? And our first step didn't get us back a lot. Okay. What was that step?
Separating the different parts of these segments so that there were 3 segments for the code, the heap, and the stack.
Right, and so actually the way we're going to do that is break it up into actually how many pieces?
4.
4. Okay. Well, we're only going to use 3 of them for a process, and as it turns out, that other one we get to use for another process. So we got back 25% because it was a fixed size. 25 versus 90%. Not a lot, is it? Turns out it's just under 25%. Okay. All right. And what did we have to do to the hardware in order to get this miracle of getting back such a small fraction of the unused space?
More registers?
More registers. In fact, what type of registers?
Pointers.
Not limit registers. More base registers. It's still a fixed size. So now we could, and the nice thing about that is now we had the ability to put these segments at different places in memory, didn't we? And the only thing we had to do was figure out what segments to memory. That's kind of where we left things off, right? Okay. Now, excuse me, and then we talked a little bit about the fact that we didn't have more. And what was the last thing we did in order to make our segmentation model more flexible? Someone who hasn't raised their hand yet. Number between 1 and 20. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15.
Can you repeat the question?
So what did we do? What hardware change did we do to get better utilization out of our segments? Okay, I'll start it off. More.
I was gonna say, I don't know, it's a mistake.
When I say more,
Oh.
aren't you the one that said it last time?
Oh, yeah, more registers.
More registers. Okay. You know what kind of registers could we have?
Were these weren't more base registers?
But we already got the more base registers, but they only got us 25% back. In order to get more of that space back, we added a different type of register. A number between 1 and 20. 8? 1, 2, 3, 4, 5, 6, 7. You know what kind of register we call that? If we already know the base,
We had like I just wrote DS and SS and DS.
and those are the base registers.
Okay, that's all I have on mine.
Okay. Santiago.
I'm sorry, I'm showing through the notes. I don't know.
Let's keep going.
I'm not sure.
Keep going.
I don't even remember what it was called.
The limit register. The job of the limit was to tell you what?
The balance of
How much you were currently using. Okay? Where you were currently using. Okay? But that gave us something we didn't want, which was what?
Variable size.
Variable size segments. Turned out we wanted variable size segments. We wanted them really, really bad because we got back about 80% of the pre-sales. Okay, but it came with something we prefer not to have. External fragmentation. Remember how happy we were that we didn't have external fragmentation? Every piece of our memory could be used for processes, so we could get more in there, so that we could have more in the runnable state, hopefully, and keep the CPU busy and the scheduler happy. And it's you know, it's weirder than that. It's weirder than that. Okay, hang on. Apple insists that I plug in the pencil for 10 seconds before we will admit that I have a pencil.
How
I
much
have
of
to do this every time I turn it on.
how much of the memory do we lose to external fragmentation after making that change?
Depends upon how memory is used.
But like on average?
It depends on how memory is used, as it turns out. And that's what I'm getting ready to draw. Is why does it depend on how memory is used? No. The app I meant, that's the app. Run the app I want, not the app I picked.
That's like,
Does your programming, do you ever do that with your programmer? No, that's not the code I meant to write. Okay. So, and this is the thing that gets weird. Okay. And it's not just that it's a rectangle. This is going to be physical memory. But I want us to think about memory over time. Is it static or dynamic? That is, does it change or does it never change?
Dynamic, yeah.
It's going to change, isn't it? At the high level, it's going to change because processes come and go. And processes are composed of segments, now of different sizes. And where they're fixed size, any segment can go anywhere. Now, you have to find a place that's big enough. Oh joy, does this sound like an order one algorithm? Yeah, we've been down this one, Mark. So let's say we have something like this. Here's our memory, and everything's in use except for these unused pieces. Okay? Or we're going to call them holes. Okay? Now, we could search through all of memory when we need to put a new process into memory and say, can we find someplace big enough? But the technique is to actually track the holes. We call this the free list. Okay? And in this case, we could do it with just a simple linked list. And then we would just have to search it until what?
Find something big enough.
Find a hole that's big enough. When we had fixed size segments, all we needed to know was where there was an empty segment, which in a linked list looks like just checking the head pointer, doesn't it? Sound familiar in terms of complexity? Is that order one? Okay. Here's another little fun problem for us to think about. I have a process coming along, and one of the segments that I want to put into memory is bigger than any one hole. But it's not bigger than the total sum of all the free memory. Sound like a problem? Okay.
Sounds like you'll have to rearrange a bunch of things.
Yeah, in fact, we're gonna use a technique. Does anybody know what the technique was called, what it said in the book? Coalescing. Another way, coalescing. I'm a visual person. Has anyone ever seen a garbage compactor? So the more common name is memory compaction. Okay, that's all. It's just going to push all the used data to one end, all the free data to the other end. Okay. In essence, it's just going to push everything, for example, up here. Right? And we do that by copying data. And since we don't know what we're going to be copying, we suspend all processes. Suspend all processes. Does that mean they're making progress towards their goal? No.
Let's do the CPU.
Is suspending processes and not letting them make any progress toward our goal the reason why we have an operating system? Okay. So there's a big downside right now to this, but it's hard to find a better solution because when we finish with compaction in an ideal sense, there's ways to optimize this. We're not going to go into that. But in an ideal sense, you only have one hole, don't you? Okay, so you only have to look at one on the list. Except once you start using that, you'll start fragmenting it up. Other programs will exit and start having holes again. So is this compaction something you're going to do rarely or frequently?
Frequently.
Turns out frequent. Turns out only do it when you need it. Well, the way I described this was you wanted to put a segment in here that if no hole was big enough there. But the available memory was. So yeah, you needed it. Could you do it preemptively? Yeah, you can do that. That's an optimization. Say, the holes are not really where I want them to be. Nobody's running right now. Let's do a partial compaction and then come back. We can do all that kind of stuff. Those are all optimizations. We're going to use the introduction in our course title and run with it. If you want to take a virtual memory design class from me, we'll spend a lot of time on this little diagram. There's probably at least 3 lectures in there. Now, stopping and compacting periodically, even if we've optimized, okay, on a system with many different jobs of different sizes that come and go frequently, okay, we're having to pause periodically. Now, on modern systems, what type of jobs do you think is the dominant job type? Interactive. So here's a question for you. I'm thinking about you. You have an interactive process. You're playing your favorite game, tic-tac-toe. Okay. And periodically it pauses for 5 seconds. You're a competitive tic-tac-toe player. You're actually practicing for the world's tic-tac-toe championships. Okay, which are Muscogee, was that Indiana? In every February 29th. Okay. That's how they weed out the weak people. Okay. Are you happy about these pauses? Okay. It's a side effect of variable size segments. Okay. Turns out to be a side effect. And it has to do with the fact that we have to, now it takes more work to allocate. Compaction is really around allocation. You could think of it as a deallocation strategy as well, but we're only doing the compaction so that we can accommodate larger allocations, right? So I prefer to think of it as an allocation strategy. So that becomes problematic. And you know what? If I gave you, except for the text segment, which we know never grows, we kind of expect heaps and stacks to grow, don't we? So when I give you your stack, like to begin with, your stack might only be 1K, you know, when you first start up your program, but it's probably gonna start getting variables and more stack frames, right? So probably just giving you barely enough will mean that the first thing you're gonna do is allocate more memory. Okay? Then I have to grow your segment, and I might have to move it, which might result in compaction. So I'm going to allocate your segments with some extra room. What do we call that extra room? Internal fragmentation. So, and it's hard to come up with a number on that. Like, how much do you give? Do you give 10% of the current segment size? Do you give a fixed amount? Do you give 4K? What do you do? This is really hard, you know, and how does that affect the number of holes you have and how often you have to coalesce, and therefore how much external fragmentation do you have? So you know how we're gonna solve this right now? We're gonna ignore it and go on to a different topic. Already people were like, you're an academic, Mark. What I want to do now is talk about how segmentation works from an address space perspective. That is, let's take a look at virtual addresses. Let's take a look at the numbers that are produced by the linker for our process, okay? Let's take a look at those. Because remember, the CPU is going to use virtual addresses, but actual physical memory is addressed with physical addresses. So the CPU is always going to admit a virtual address. Okay? So we have our CPU up here. And when it accesses memory, and the phrase just because I've used it for forever, I say it emits a virtual address. Just means it references something. Okay, whether it's a load or a store, it doesn't matter. Well, we've got a virtual address, which I'll almost always from here on out call a VA, a virtual address. And then a physical address will be a PA. And PAs point to PMEM, and VAs point to VMEMs. Okay, got that? Everybody got that? All right. And the secret handshake is lots of terms floating around. Lots of terms floating around. If they get confusing, stop me. Okay. So now we've got this virtual address that's going to be sent out, and eventually, out here we have our physical memory, and it's going to be accessed with a physical address. Okay? And the question is, what happens in between? Now, what happens in between is going to be called the virtual address translation. Okay? It's the virtual address translation process. And we're going to talk about it as it relates to segmentation. Now, the virtual address comes in, and the first thing we have to figure out, remember how I said last time that we'll kind of use limit and bounds interchangeably? What I'm going to do is explain to you why they're different for just a quick second, and then we're going to ignore that. We'll use the general term after that. If you have a limit register, that says what's the highest address that I can have in memory, in physical memory for this segment. Okay. And so that would mean we take the virtual address, add it to the base register, and compare it to the limit register. The bounds register tells you what the maximum offset is into memory. So we take the virtual address, compare it to the limit register, and if it's within that bound, because it'll be 0 to that value, then we say it's it's valid. So it's where do you do the addition, before or after the check for bounds? Okay. So let's just say that what we're going to do is we take the virtual address, okay, and we're going to compare it against, which is called the bounds register. We call it the limit register. As I said, you can call them either. Okay? If the virtual address is greater than that register, what do we know?
It's out of bounds.
It's out of bounds, but what do we mean by out of bounds?
Not within the given segment.
Not within a given segment?
It's trying to access memory from outside of its scope.
Not outside of its scope. We're really close. I'm going to say, let's say it's outside of its allocated address space. We're going to talk about a thing called a maximum segment size here in a minute. And that's why I didn't want to say it was outside of its segment. We'll see that in a second. Okay? And if it's an error, what do we know? What do we call it?
Segmentation.
Segmentation fault. Seg fault. It's not in an allocated segment. Ah, die. Sorry, I grew up with Looney Tunes cartoons. And then all I would have to do is if it passes, we just say VA plus base register equals physical rest. Right? That's fast, isn't it? We can do that in about 4 machine cycles. But to get simplicity, we had to have what I call pain and agony. To get efficiency, we have to have complexity. In order to get simplicity, it's going to wind up being less efficient. And that's why we've got both internal and external fragmentation right now. We're not going to fix external and internal fragmentation until we get to paging. The system I've given you so far for thinking about external and internal fragmentation is what it is for segmentation. It doesn't get any better. Okay? I mean, you're like, but I'm paying so much money for this computer science education. Okay. It's one of the reasons why segmentation is more heavily used than paging is used more often than segmentation. So now we have a very clean, very quick way to do our translations. All right? And this works out pretty good. But there's some things we haven't really quite talked about. And now what I want to do is, no, come on, let's go. No. Over here, no. Come on, you, come on. There we go. Let me get a new slide. There we go. What I want to do now is take a look at addresses. In order to make it for 2 things. One is we're going to shorten the instruction set architecture to 14 bits because 32 bits, most of them are going to be zeros, so we'll just shorten it. It's easier to write out, harder to make mistakes. And the second reason why we're going to do that is because Mark should have been a pharmacist with how he writes. Okay? I don't want everyone, like me, where I have bifocals, but I have to turn my head like this to read my writing. So I prefer that nobody wound up with worse eyesight because of me. But if you do, it's a benefit of taking courses here at Portland State University. So how many of you read the book? How many of you saw the segment translation example? We're going to do it. Talking about this, there are many subtleties with it. And merely talking about the theory of it is not going to expose you to what the real pitfalls are. So we're going to work an extended example. And yesterday we found out that there's a couple bugs in the book, but we'll fix those as we go on. And we go through it, we're going to see what the different steps are and what is the impact of having a segmented architecture. And one of the things that's the impact is very negative. We haven't really talked about it yet. We've mentioned it, but we haven't talked about it yet. Okay? You guys remember from CS201 talking about the compilation process? How many of you remember looking at that picture of the ELF file format? How it was loaded in memory? And if you took it from Professor Wusong Fang, he said, oh, there will be a test question on this. If you took it from me, I said, you'll never have a test question on this. You can ignore it. Okay. In general, the ELF puts things into different segments. It's the same type of segment. And ELF tends to have many, many segments. We're not going to do that. We don't need many, many segments to learn how this works. We're going to stick with our standard 3 segments. It'll also make the issue much more obvious. Okay. How many of you are like, okay, let's go. We're at the top of the roller coaster. We can't get off now. Ooh, look, I found a big hole. All right, so what we're going to do is we're going to use a 14-bit address space. Okay. Now, that means pointers are 14 bits. Memory addresses are 14 bits. Okay. Are memory addresses signed or unsigned? Unsigned. Okay. That's going to become important in a little bit. So let's do a 14-bit virtual address space. Okay. Because the size of the architecture is the size of the virtual address space. Now, we can have a bigger physical address space, and that's going to be useful. And so we'll do that. We'll say it's maybe 4 or 8 times as big as this. Okay. We only need it at the very end. Now, what we need to know about here is for which segment, what's the base address, what's in the base register, right? And then we need to know how big it currently is. You see how I didn't say bounds or limit? You see how I avoided that? I just said how much space was currently in this. And this is how we'll continue to talk about it. We won't say what is the value of the limit, what is the value of the base. I mean the value of the bounds. We're just going to say how much is in use, which is different than how big can the segment be. We're going to talk about that right now. So we're going to have a virtual address, and it's going to begin at bit 0 and go to which bit? 13. Now, the virtual address has to give us the ability to select the correct segment. Okay? And we're going to do that using a technique